The 1981 Internet Protocol was built on a strict philosophy of end-to-end transparency. In this original architecture, an intermediate router had exactly one job: look at the destination address and forward the packet. The contents of that packet, including its source identity, arrived at the destination exactly as they were created, straight from the source. By 1992, the engineering community realized this elegant model was on a collision course with basic mathematics. The commercialization of the World Wide Web meant the 32-bit IPv4 addressing scheme, which capped out at roughly 4.3 billion unique identifiers, was going to run dry. To prevent the global routing table from collapsing, the Internet Engineering Task Force published RFC 1631 in 1994. It outlined a temporary palliative called Network Address Translation, or NAT. NAT relied on the concept of the stub domain. Engineers realized the vast majority of computers on a corporate or residential network only communicated locally. By assigning these internal machines non-routable private addresses, an entire local network could hide behind a single router holding one globally unique public IP address. This animated diagram illustrates the cost of that conservation. While the original architecture passed packets untouched, a NAT router intercepts the packet, violently cracks open the IP header, and overwrites the source address before sending it upstream. This modification immediately triggers cascading errors in the transport layers above it. Masking entire networks behind a single IP address kept the internet functional for decades past its expected expiration date. But it also replaced the transparent end-to-end model with a state-dependent hierarchy, imposing a heavy engineering tax on every layer of the global network stack. The earliest form of this technology was Static NAT. A network administrator configured the border router to maintain a rigid one-to-one mapping between a private internal address and a public external address. A strict one-to-one mapping does not solve global address scarcity. If an office has 1,000 computers, the organization still needs 1,000 public IPs to connect them all to the internet simultaneously. The solution to this scaling problem was port address translation, commonly known as NAT overload. This translation table shows PAT multiplexing thousands of sessions onto one public IP. The router modifies the source IP and the 16-bit source port, creating a unique socket. For return traffic, it reads the destination port, queries the state table, and routes data back. Because the 16-bit port field allows for up to 65,535 concurrent ports, a single IP address can theoretically handle tens of thousands of active connections at once. To achieve this scale, enterprise routers had to abandon their roles as stateless traffic directors. They were forced to become memory-intensive state machines, actively generating, storing, and purging temporary records for every single website visit, email check, and background sync occurring inside the network. Swapping an IP address in a packet header triggers a computational cascade. The Internet Protocol Suite relies on checksums to guarantee data integrity, ensuring bits aren't fripped by faulty hardware during transit. The transport layer protocols, TCP and UDP, calculate their checksums using a pseudo-header. This pseudo-header mathematically bakes the source and destination IP addresses directly into the transport layer's validation check. When the NAT router overrides the source IP, the TCP checksum fails and the packet is dropped. To avoid recalculating the entire payload's checksum, the router uses one's complement arithmetic. It calculates the mathematical difference, the delta, and applies it directly to the existing checksum, patching it. Even with this mathematical shortcut, rewriting headers and updating transport checksums demands continuous, heavy CPU cycles. Hardware that was designed to simply read and forward must now perform active arithmetic on millions of packets per second. The math gets harder when protocols hard-code IP addresses into their actual data payloads, completely bypassing the standardized headers. The File Transfer Protocol, or FTP, establishes data channels using a port command. The client sends its own IP address and listening port to the remote server, encoded as a simple ASCII string deep within the TCP segment. In this scenario, we see an FTP packet arrive at its destination. The NAT router correctly updated the IDER IP header, but it ignored the payload. When the remote server unwraps the payload and attempts to open a connection back to the listed address, it hits a non-routable private IP and the session dies. To prevent this, NAT implementations require application layer gateways. An ALG intercepts specific protocols, digs into the application data, and rewrites the payload on the fly so it matches the public mapping. Modifying an ASCII string creates a cascading sequence error. Translating a short private IP like 10.0.0.1 into a longer public IP like 198.76.29.7 changes the physical character length of the payload, altering the byte count of the entire packet. TCP relies on precise sequence and acknowledgement numbers to keep data streams synchronized. Once the ALG changes the payload length, the router must recalculate the sequence numbers for every subsequent packet. This prevents the connection from tearing itself apart. With application layer gateways, NAT actively violates the highest levels of the OSI model. Routers act as invasive middle boxes, editing the user's application data and forging the transport synchronization just to keep legacy protocols functioning across the boundary. Network address translation and cryptographic security have opposing goals. Internet Protocol Security, or IPsec, assumes end-to-end transparency. It is engineered to detect and reject any intermediate tampering. The IPsec authentication header creates a rigid cryptographic hash that seals the entire packet. Crucially, this mathematical lock incorporates the source and destination IP addresses. Watch this IPsec packet pass through a translated network boundary. When the NAT router fulfills its basic function and modifies the source IP, it shatters the cryptographic hash. At the destination server, the tampered header registers as a malicious man-in-the-middle attack, and the packet is automatically dropped. Even protocols like encapsulating security payload, which leave the IP header unencrypted, fail because the NAT router cannot access or update the TCP checksums hidden beneath the encryption layer. To resolve this, the industry created IPsec NAT traversal. It encapsulates the fully encrypted IPsec packet within a disposable UDP header. At the NAT boundary, the router only modifies the disposable shell. The inner encrypted packet remains untouched and is successfully verified. NAT traversal forces the global internet to wrap secure data inside redundant, inefficient packet layers, expending bandwidth and compute power simply to survive the crossing of a translated network boundary. In 2011, the global free pool of IPv4 addresses officially ran out. Internet service providers and mobile carriers could no longer issue unique public IPs to their customers, forcing them to deploy translation at an infrastructure-wide scale. This macro-topology shows carrier-grade NAT. The user's router receives a shared private address. Traffic passes through the home NAT, then hits a massive carrier core NAT. Here, millions of subscriber sessions are aggressively funneled into a restricted pool of shared public IPs. Burying devices behind two distinct layers of translation functionally destroys true peer-to-peer networking. A device in this environment cannot act as a server because it has no reliable way to receive unsolicited inbound connections from the outside world. Latency-sensitive applications like voice-over IP and video conferencing function by relying on complex traversal frameworks. Frameworks like stun, relays like turn, and paths like ICE force devices to constantly ping external servers to discover their public IPs and keep pinholes open. Carrier-grade NAT stripped away the final remnants of client autonomy. Real-time communications on the modern internet require continuous reliance on centralized third-party relay servers to navigate the translation layers blocking direct access. The migration to IPv6 provides a theoretical address space of roughly 340 undecillion identifiers. By sheer volume of available numbers, address conservation techniques are obsolete. Yet, despite having infinite addresses, network engineers are still actively standardizing new, highly complex translation architectures for the IPv6 era. This side-by-side architectural flow illustrates two of those systems. On the left is the 464XLAT process, a requirement for mobile networks to translate legacy applications with hard-coded IPv4 addresses over a purely IPv6 core network, using a double translation mechanism. On the right is Network Prefix Translation, or NPTv6, heavily utilized in enterprise environments. Unlike traditional IPv4 translation, it uses an algorithm to map internal addresses directly to global prefixes, statelessly, maintaining a strict 1-to-1 ratio and preserving the original payload checksum without modification. Network prefix translation exists entirely for administrative control. By translating at the boundary, an organization decouples its internal network topology from the IP assignments dictated by upstream internet service providers. Without prefix translation, switching ISPs, establishing redundant multi-homing, or executing a corporate merger would face the labor-intensive risk of renumbering thousands of internal host devices. Network address translation survived the address exhaustion crisis because it proved too useful to abandon. The Internet permanently traded end-to-end transparency for administrative leverage, privacy abstraction, and routing flexibility. Whether through stateful multiplexing or algorithmic prefix mapping, the ability to control and rewrite network identity at the boundary is an engineered compromise built deep into the foundation of the modern Internet.